All right. So hopefully kind of the day off on Tuesday was good. We're going to finish up confidence intervals today, and then we'll move on to the next topic, which is hypothesis testing. I'm going to put up a Learn Smart assignment after class today. I want you guys to complete before we meet on Tuesday. All right, so before class starts on Tuesday, you'll have another Learn Smart. So no online quiz today, just kind of get on 10, 15 minutes on that Learn Smart, kind of get us ready. We'll talk about it some today, but get us kind of prepared for hypothesis testing next week. And then kind of the original exam date, if you look at the syllabus, was supposed to be tomorrow. Obviously, like I haven't mentioned it because we kind of postponed the first one. We're going to push the second one off a little bit. So it'll probably be the beginning of not next week, but the following week. So we'll finish up hypothesis testing next week. That's all we'll pretty much talk about. I'll get some review materials up. They might not come up or show up on Canvas until tomorrow, but I'll get some kind of practice exams, kind of like the last one up there. So we're kind of moving our way towards that, right? So hypothesis testing will be the very last thing we talk about, which will be all of next week. We should have plenty of time to kind of get through that and then kind of prepare kind of towards the end of next week for that exam, okay? And we'll kind of see, hypothesis testing really takes a lot of what we've already talked about and just kind of, it's kind of the culmination. Okay? So where we left off last class, we were talking about kind of what happens when we don't know the population variance, right? You know, we build all these confidence intervals for where the true population mean was, but our standard deviation of our sample means needed the population variance. Well, that doesn't seem very likely, right? How do I know the population variance, but not the population mean? We kind of worked through, and I kind of showed you that student T table and how we use it, right? And then kind of we ended on, here's going to be our equation for the confidence interval for when we're trying to build a confidence interval where the true population mean lies, but we only have this sample variance, right? So the notation was a little bit different, where the standard deviation of our sample means, instead of sigma now, we write S, because we're not calculating that using a population variance, we're calculating that using a sample variance. Okay? So, you know, our steps are going to be very similar to what we did before. It's just now we're using that student T distribution, and we'll work through a couple examples today, so we'll get more practice with that. But really the format of the equation hasn't changed at all. Okay? So let's start out with an example, kind of have some numbers to kind of put to this, and I'll kind of walk us through it. So let's say we don't have a known population standard deviation, it's unknown, right? So we take a sample 36, we calculate the sample mean and the sample variance from those 36 observations, okay? If I want to build a confidence interval that corresponds to an alpha of 0.01, just kind of a little refresher, we've been kind of off for a while, an alpha of 0.01 would be a confidence level of what? Right, so alpha is the area outside my interval in decimal form. So if the area outside the interval is 0.01, the area inside my interval is 0.99. So yep, 99%, okay? So what's the setup gonna look like for this? I'll switch over to the dot cam here real quick. Maybe real quick. There we go. So the setup we have is we were given this sample mean, we calculated our sample variance, and we had our sample size. We were also given that the level that we want is alpha of 0.01, or we said kind of the 99% confidence level. So the equation that we eventually are going to have to use, we left off last Thursday, looked something like this, where that standard deviation of my sample means is the same as it was before. It's just now I'm using a sample variance instead of a population variance. So what that means is, right, we no longer can use a standard normal distribution. We have to use a student T distribution. And it's going to be a little bit more spread out, we said. Like the variance is higher than 1. So we can't use the same values that we were using for this standard normal distribution, but the setup is still the same. We want to find this value from a student T distribution such that the area outside of our interval, or kind of in the tails, the total area is alpha, which means there's alpha over 2 in each tail. So here our alpha is 0.01 divided by 2. We have 0.005 in each tail. Okay? So, up to this point, like there's been a little bit of different notation, but really the process of what we're doing hasn't changed. It's just now we have a different distribution. So we want that area of 0.005. So we have to go back. Instead of using the standard normal z tables, oh, thank you. I shouldn't have to switch it after this. There we go. So instead of the z tables, we're going to have to use the student t tables, right? Because we're using a student t distribution. So the way that we use this, we go up to the top. This is going to be, and kind of this little picture, oops, up here reminds us, the student t table looks at the right tail, right? Or kind of the right side of the distribution. So it actually makes it a little bit easier for us because when we were doing confidence intervals, we said there was this negative and positive value, they're the same, but those signs are already built into our confidence interval equation. Okay? So now we're just getting the absolute value. So that kind of makes our life for confidence intervals a little bit easier. So the area we want in this tail is 0.005. So we're going to use this last column, right? This column heading represents the area we want in the tail. Okay? So 0.005, but one thing we have to now calculate, I didn't kind of write it in here, but if we go back in the slides, we also need our degrees of freedom. Because each, right, there's not one student t distribution, every single degrees of freedom is a different student t distribution. So if we have our sample size, our degrees of freedom should just simply be that sample size minus 1. So here we've got what? 36 minus 1 or 35. So our degrees of freedom is 35. So we'll scroll down here. Degrees of freedom 35. The area we wanted in the tail was 0.005. So what? 2.724. So what we just found was this t value that gives us alpha total in the tails, or alpha divided by 2 in each tail. Okay. Any questions about how you can use that table? Like I know we went over it towards the end of class, but it's kind of still new. No, nothing in the chat. Okay. So now we've got that student t value. Now it's just a matter of really of plugging everything in. So our sample mean, if we want to get our upper bound, we'll take that sample mean, right? I'm just plugging that in. We'll add that t value times. Now here's where we could plug everything all on at one time, right? I could kind of plug that formula in, write it all on one line. I think it's probably easier to calculate it separately. So down here, if we think about what's the standard deviation of my sample means, well, that's the square root of my sample variance, which if we go up was 324, divided by my sample size. So notice when we're calculating the standard, and this is all within the square root, when we're calculating that standard deviation of my sample means, that's still based off of the sample size. The only time we use the degrees of freedom is when we go to that table, right, to identify the student t distribution that we need. So I, could plug this in. I think if I remember right, if I'm doing the math in my head, this ends up being 3, right? So then I just plug that value of 3 in, right? And then the lower bound is the exact same thing, but we're subtracting, right, that margin of error. Okay? So like I said, the setup is the same, it's just now we have to use this student t distribution. Okay? Which gives us, I guess, kind of another statistic, which is we have to calculate the degrees of freedom in order to identify the correct student t distribution. Okay. Any questions on that? We're going to work through another example here as well, and then do another example in Excel. So let's go back to the slides. All right, and we kind of I worked all this out by hand, but really what did we do? We identified what the problem gave us. We looked up that student t distribution. We calculated this intermediate step, right? I said you don't necessarily have to do step 3. You can kind of plug that in. Notice I kind of wrote this a little bit differently. There's 2 ways we could write that. Let me show you that real quick here as we have it pulled up. So right? If I plug the equation for what that standard deviation of my sample means is into here, it looks something like this, which we could also simplify that. Another way of writing this mathematically would be that, right? So all are kind of, we'll all get you the same answer. It's just, if you were given the sample variance versus the sample standard deviation, one of these would be a little bit easier, right? Now, even if you were only given the sample standard deviation, you could still plug that in here, square it, and calculate it just fine. So I usually don't kind of write out this equation here because more often than not, we're going to have the sample variance. So if you want to do it all at one time, this is probably the formula you're thinking about. If you want to calculate that intermediate step, which is usually how I'll work these out because I just think it helps helps us see the steps, this is the guide that we want to use, okay? So we end up, once we do that calculation, we get our lower and our upper bound here. So this is kind of an interesting confidence interval because, this example didn't have context, but maybe if this was like the return on, some type of investment, what we could say here at the 99% level, remember, because alpha is 0.01, at the 99% level, we know that the true mean has to be somewhere in this range, which means the true mean or the return on this investment would be positive, right? Which might, might be important to be able to say, right? That whatever this investment is, the true mean return is going to be some positive value, if that was kind of the example we had. I just wanted to give us some numbers first, maybe no context to them to work through something. So what if instead we have this example where the American Medical Association states that the average, I think this was starting salary for physicians, is $175,000. You think maybe it's something different, so you want to build a confidence interval. You take 81 physicians, you get a sample mean of 160,000 and a sample variance of 324 million. So we want to build the confidence interval for where the true population mean lies, right, based off of what we saw from our sample, at an alpha of 0.05, which would correspond to right, alpha is the area outside my interval, so this would be a 95% confidence interval, right? The area inside my interval would be 0.95. When we say confidence, what's the confidence level? We say as a percent, so 95%, okay? So that's kind of the setup. So let's just start kind of working through this. First step is always, okay, so what do we have given to us? We found a sample mean of 160,000. We had a sample variance of what? 324 million. My sample size was 81 physicians, and alpha was told to be 0.05. Well, the first thing I could do right away is just, well, I know that I only have this sample variance, so I'm going to need my degrees of freedom. Nope, sorry. 81 minus 1 is 80. I was thinking ahead there. Okay. So the next step is, well, I know that I need to use this equation. Part of that is I need to find what that t-value is. Okay. So I'm looking at a student t-distribution because I only have the sample variance, and I need the t-value such that the negative and the positive of that would give me alpha total in the tails, or alpha over 2 in each tail, which what? 0.05 over 2, 0.025. At a degrees of freedom of 80. All right. So the next step, and let's see, awesome. We go to our student t-table. The area we want in that upper right tail, we said was 0.025, right? 0.025 in each tail. So we're going to be using this column, and our degrees of freedom is 80. So we start scrolling down, degrees of freedom, getting higher and higher on the left side there, 80. Right? So we go over the t-value that would give us 0.0225 in each tail at a degrees of freedom of 80 would be positive and negative, kind of 1.99 there, right? Any questions up to this point? Okay with this? Okay. So let's finish this out, right? I can then calculate that intermediate value, which is the standard deviation of my sample means. So it's going to be what? The square root of 324 million divided by 81, my sample size. I think, and we'll see on the slides if I'm remembering this correctly, I think this works out to be 2,000. Okay. At this point, it's just a matter of plugging everything that we have into this equation, right? So let me see if I can get this side to side here. Oh, I gotta move this. So our sample mean was 160,000. We'll add to get our upper bound. The t-value we need is 1.99. And that standard deviation was just 2,000. And then to get the lower bound, it's the exact same thing, but we subtract that margin of error, okay? Any questions? Now at this point, right, this is a pretty easy thing to get into our calculator, okay? Any questions on that? So, it's kind of what I have outlined here, all the work that we just did. And if we actually do those computations, we get what? 156 to about 164,000. So this is an interesting one because if we think about what we have, we just found, and you can kind of see this through here, so let me move that. We just found this confidence interval at the 95% level goes from about 156,000 to about 164. I'm rounding a little bit here. But remember, the problem started out with saying the American Medical Association said that the average starting salary is 175,000. Well, that's far outside of our confidence interval. So at the 95% level, we could go to them and say, well, look, based off of our sample, with 95% confidence, I can tell you that that number that you're saying isn't right. That number is wrong, right? You're reporting an incorrect kind of mean starting salary. And I could be wrong, right? I'm only 95% confidence. 5% of the samples I see, I'd end up with a confidence interval that doesn't include that population mean. So this very well could be the true population mean. There's a 5% chance that I'm wrong. But there's a 95% chance that the true value is somewhere in this range, okay? So you can kind of see, building these confidence intervals, we can start to make statements about, or we can at least start to kind of almost like fact check, right, some of these reported mean values. Okay. Any questions on that before we keep moving? Because the next thing we're going to do is we're going to see how we do this in Excel. We've already done other confidence intervals in Excel. It's going to be pretty similar to what we did before. There's going to be like one new thing that we have to do. Okay. Check the chat. All right. So move this out of the way here. And I've got kind of some of the equation or kind of a summary of what we're going to do, but let's just jump into it. So we had this confidence interval example, and I did, I originally posted the original file. We did some additional stuff in class. So if you're working through that Excel homework, the original file I posted is probably the best template because it's just a little bit cleaner. But we did some extra stuff here that we didn't need to do. I showed you how to use the if statement. We built the confidence intervals in 2 different ways, so I could show you that there's multiple ways to do it. But if you're just kind of looking for one clean version, that original one I posted is probably one to go on. After class today, I'll repost this and call it, confidence interval example in class work, and we'll have some of the additional work in that file that you can also look at. Okay? So we're going to deal with this unknown pop SD kind of, or unknown population standard deviation worksheet today. So I've got this data where it's got drug deaths in different counties in the year 2012, and then another data set over here where it has those same counties and the drug deaths in 2016. Okay? So we're going to use this drug deaths kind of per 10,000. You can kind of think about it, if it's easier, it's the drug deaths per capita, right? We're factoring in that, a county that's a lot smaller isn't going to see as many drug deaths as a county that's a lot larger. Okay? So we come over here. I'm going to delete this for a second. So these t-values in the upper and lower bound, and show you how I kind of created those. So the first thing we're going to need is our sample mean, our sample size. We can think about this was n. And then I have variance here, but just to be a little bit more specific, I'm going to be calculating this based off of my sample. So this is really only a sample variance, right? I go over here, I just have a sample of counties in 2012. So what I'm going to do is use that average function to find the sample mean, right? That should be kind of old hat at this point. The count function to find my sample size, just count and then select that variable. And then var.s, we've used that before, we're going to calculate a sample variance, right? A variance based off of this sample. Okay? So we've got 3 of the components we need. The other thing we need is, okay, what's our alpha? Well, we're going to build 3 different confidence levels. Remember, this is like the 90, 95, and 99% confidence levels, right? That's what those alphas would correspond to. So before, when we had a known population standard deviation, just as a reminder, if I can, there we go, we were calculating a z-value, right? Because we knew that we could use the standard normal distribution when we had that population variance. When we only had a sample variance, when we start to create what we thought would be z-values, well, we have that n-1 in our sample variance, and so the resulting distribution is actually not a standard normal. It's still normal and centered around 0, but it has a little bit higher of a variance, right? We have one of these student t distributions. So before, what we used was that norm.s.inv function, because we knew the area that we wanted in the tail. Well, it's going to be almost, whoops, Control Z there. It's going to be very similar, but we're not using the standard normal distribution, not norm.s now. We're using the student t distribution. So we'll use t.inv. We still tell it the area that we want in each tail, which is alpha divided by 2, comma. Now, though, we have to tell it one more thing, which is, well, there's a lot of different student t distributions. Which one are you using? Which is identified off of the degrees of freedom. So one thing to be careful about here is it's not simply telling it the sample size. You need to tell it the degrees of freedom. So it's the sample size minus 1. Okay? Any questions on this point? So this is going to be great, right? With a couple exceptions. One, we're always telling Excel the area in that left tail. So we looked back, I kind of had that ABS in there. It was because, oh yeah, the signs are already built into my lower and upper bound equation. I just want the absolute value, right? So I could use the absolute value function, which is probably the easiest way to do it. We said another way we could do this was, well, if there's alpha over 2 in each tail, then if there's alpha over 2 in the upper right tail, right, what would the area to the left of the positive t-value be? Well, if there's alpha over 2 here, the area to the left would just be 1 minus alpha over 2. So we could use that absolute value function, right? And that's going to give us 1.65 here. Or we could, I'll get rid of those parentheses, do 1 minus alpha over 2. And we get that same value, right? So there's 2 different ways of doing the same thing there. And it's the same thing that we were doing when we had a known population standard deviation, right? Either using that absolute value function or 1 minus alpha over 2. Okay. All right, so, you know, I can copy this down and my cell reference for alpha will update, so that'll be great. But so will my sample size reference. And I want to keep that, you know, the same, so I'm going to have to freeze or put $signs around that. Now when I copy this down, it'll keep using the same sample size to calculate the degrees of freedom, but for these next, you know, different confidence level intervals that I want to build, it'll update the alpha, right, that corresponds with those different confidence levels. So now when I copy this down, now I've got my 3 t-values, right? I've got the t-value that would give me 0.005 in each tail, or a total of 0.01 in the tails. I've got the t-value that would give me 0.025 in each tail, kind of the original one we had, which was 0.1 total or 0.05 in each tail. So this was basically, this is replacing the step of looking this up in the table. right? Excel is like looking it up in these tables that it has stored in it. And it's really not just storing the tables, it's doing some integration and kind of getting the area under the curve for you. But for the sake of what way we think about it, you can think about it has all these values stored in it. Well, now we've got, right, we've got our sample mean. We've got our t-value. We need the standard deviation of our sample means, which we can calculate because we have the sample variance and the sample size. So what I'm going to do is up here, is calculate that intermediate step, which is the standard deviation of my sample means. Okay. So this is going to be the square root of my sample variance, which is right here, divided by my sample size. Right. Once I have that, it's pretty easy, right? My lower bound is going to be, take my sample mean, subtract that t-value, which is right here, multiply that by the standard deviation of my sample means, which I have right here. Okay. So easy enough, right? And I get my lower bound. Now the problem is, if I just try to copy this down, what went wrong? Oh yeah, it started updating that sample mean and the standard deviation of my sample means. The only thing I really want to update when I'm building different levels of confidence, the only thing that's going to change is that t-value. Okay? So I go back to the original one. So the only thing I want to change when I copy this down is that t-value. So I'm going to freeze my sample mean cell reference and the standard deviation of my sample mean cell reference. That way, when I copy this down, right, I'm building the confidence interval around the same sample mean, and that distribution still has the same standard deviation. It's just if I want a 99 instead of a 90% confidence interval, I'm going to have a different alpha value. That's going to give me a different t-value. So that's the only cell reference I want to update when I copy this down. So when I copy this down now, okay, now it looks like it's, yep, working correctly. Same sample mean, same standard deviation of my sample mean, and now I've got this new t-value. Okay. Now, when we want to do the upper bound, probably the easiest way to do this, right, I just double click on this lower bound. I'm going to highlight the formula, and I'm going to copy it. To get out of the cell, I'm going to hit enter. That's probably the best way to do it. Then I'm going to go over to my upper bound. I'm going to paste that formula. When I copy and paste in this way, none of the cell references change. And that's exactly what I want. I want the exact same formula for the upper bound, but instead of subtracting that margin of error, I want to add it. All right, so all I have to do is change the sign there. Now when I copy this down, I can get my upper bounds as well. And then I've got my three confidence levels, or sorry, three different levels of my confidence intervals. Okay? Now, kind of remember, what do we have here? Well, this is a 99% interval. If I want to say something with less confidence, that means the area in my tails, right, alpha is going to actually be higher, which means with less confidence, I need a smaller t-value, which means my confidence interval will be more narrow, right? So if we look here, when I'm going to lower levels of confidence, notice my lower bound gets higher and my upper bound gets smaller, so they're kind of coming closer together. So I have more narrow confidence intervals at the lower levels of confidence and wider confidence intervals when I'm looking at higher levels of confidence. It's kind of relating to some things that we've talked about in the past as well. Any questions to this point? Okay with this? Okay. You know, and I did some things down here where I looked at, okay, what about 2016, right? So now I just used a different variable. I calculated the sample mean in 2016, and you can kind of see, well, the mean, the sample mean I found in 2016 is higher than the sample mean I found in 2012. However, if I think about these confidence intervals, and I just plot these points for 2012, and I'll switch over and zoom in a second after we get these numbers written in. So in 2012, I had what? Let's just do the 90% confidence, so 2.16 to 2.73. So the true population mean in 2012 could be anywhere in this range. Right? If I then think about plotting the confidence interval for 2016, it goes from 2.19 to 2.8, if we round it 1. Okay. So even though the sample mean was higher in 2016 than it was in 2012, those confidence intervals overlap quite a bit, right? Even though it was higher, they were very close to each other. So our confidence intervals overlap a lot, and the true mean for 2016 could be down here, which would actually mean that these drug death rates have decreased, but it could also be somewhere up here, which would mean that they've increased, right? So when we have this much overlap in the confidence intervals, we really can't make any statements, right? Or at least not at the 90% level here. What we would need is something like this, where 2012 and 2016 had no overlap. That way, even if the mean in 2016 was the lowest in that range, and the mean in 2012 was the highest in that range, well, we could still say at 90% confidence that drug deaths have went up, right, from 2012 to 2016. So if they do overlap, the confidence intervals do overlap, we really can't say anything. The only time we can really make statements comparing two groups, or in this case 2 years, is if we have no overlap in those confidence intervals. Okay. Any questions on that before we keep moving? Or anything about anything here in the Excel? And also you'll have like an example here. I didn't calculate the intermediate step. I just built it all into the same formula. So you kind of have an example to look at if you want to do it that way as well. Like I said, I think the easiest way to do it is how I showed you here, calculating the intermediate value, because that really simplifies, finding that lower and upper bound once you get to that point. Yep, so I have the original files been up there as we've been working through it. I think, I can't remember if I was waiting until after today. I know from my other sections it is. So let's make sure so I can identify where it's at. So we're working off of this file. Yeah, I'll, actually, I can do it right now. So we'll save this. Yep. Let me get this posted right now while I'm thinking of it. Let me change, oops, I didn't want to do that. Let me change the name real class. So we'll put in class work. Right? So if you're looking at the files, this confidence interval example, it's cleaner in the sense that there isn't additional work that you're not going to need to do for that homework assignment. So I would probably work off of this one in terms of I want my assignment, kind of the format or like the look of it to look similar to this. However, right, this one's fine. Like there's a lot of like everything that was in this file was, well, everything that was in this file was is going to get you the correct answer. It was just I showed you like multiple ways of doing it, right? The intermediate step versus not. So which one's better? If you watched me work through it in class, honestly, probably the one that has the in-class work, because you're going to know what everything means. If you missed that class, or you weren't, you haven't seen me work through it, or you weren't watching me work through it, you didn't watch the video, there's going to be a lot of stuff in that file that you're like, well, wait, what do I need to do this too, or do I need to, you're not going to know it was like some additional work that we did. So, it kind of depends on if you watched me like today, you guys probably use the one that I just put up there, right? That were the work that we did in class. That's probably the easiest one. Okay. All right, any more questions before we keep moving here? And, both those files do have a worksheet that we didn't work off of, which is this first one. And it's just another example with a different data set, which, is kind of cleaner. So you could look at this one as well, just for some additional help, but there's really nothing here that we didn't do in the other files. It's just another example. Sometimes I like, it just depends on what we've talked about, which data set I like to use. Yes, yeah. This is questions, 2 through 4 is pretty much all confidence intervals and will come from that file. The very first question goes all the way back to when we looked at the Indiana weather data file, where we were really just getting used to using that norm.dist function to like find the probability of being above or below. Like we had a known population mean, right? We weren't dealing with these situations where we don't even know where the population mean is yet. Yep. All right. So for the sake of where we're at with time and where I want to get us, I might go through some of these files or these slides pretty quick, but there's really a lot of stuff we don't necessarily need to spend a ton of time on. So the next thing we're going to do is hypothesis testing. Right? So with confidence intervals, we were trying to narrow down where this true population mean was. And I kind of showed you, we could check certain values. If those values weren't in our confidence interval, we said those can't be the population mean. So with hypothesis testing, we're going to test very specific values. Okay? So we don't know where the population mean is, or we could do the exact same thing, but for the population proportion. That's something we'll probably kind of work through next Tuesday. Right? Well, next Tuesday's class. So what we're going to do is develop what we call the null and alternative hypothesis. Right? So all the null and alternative hypotheses are, the null hypothesis is saying, I'm going to assume that the true mean is somewhere in this range. And that maybe I say that it's greater than a certain value, that maybe I say it's less than a certain value, or I could even say, I'm going to assume it's equal to this one value. So the idea might be, I'm going to assume the average income in the US is greater than or equal to 50,000. That would be my null hypothesis. That's what I'm assuming is true. The alternative hypothesis is basically the complement of that, the exact opposite. So the alternative hypothesis would be that it's less than 50,000. Right? We're then going to take a sample, and if I see sufficient enough evidence that goes against my null, against what I assume to be true, then I'm going to reject it, right? If I assume that the average income is greater than or equal to 50,000, I take a sample and I see a sample mean of 35,000, well, I'm going to look at that and say, based off my sample, what I assume to be true is not correct, right? Because I found 35,000, that does not fit with what I assume to be true, which is that it was greater than or equal to 50,000. Okay? If we don't, have sufficient enough evidence, so maybe I see, 55,000 as my sample mean. Well, that actually supports the null, so I'm not going to reject it. I could see 49,000, which goes against my null, right? That's not greater than or equal to 50,000. But if the true population mean was 50,000, 49 would be a very likely sample mean for me to see, right? It's not very far away from it. So we need to have sufficient enough evidence, right? So kind of the example that we'll be working through a lot today is I'm going to be assuming that I want to test for whether or not the average mass market beer has a lower ABV than 7%. So what we want to test for, or what we're trying to find, that's our alternative hypothesis. We'll stack the deck against ourselves and assume the opposite is true. So here, if I want to find, is the ABV of the average mass market beer less than 7%, the complement of that, I'm going to assume to be true, which will be my null hypothesis, is it greater than or equal to 7%? Okay. We could then take a sample. We might see a sample mean of 4.5. Well, that goes against our null, but does it go against our null enough? Is it sufficient enough evidence? And that's what we're going to try to get to by the end of today, to see how do we determine whether or not it's sufficient enough evidence. Okay? So the way that, we write this, and here's some formal definitions. I've already kind of explained this, but H subscript 0 is our null hypothesis. And that null hypothesis, we said, that's our assumed true state of nature. What we're assuming is true. H subscript A, we're going to use that as the alternative hypothesis. Now, if you're looking at the book or maybe the next Connect homework, which we won't have one prior to the exam, but we're going to do some hypothesis testing before the exam and some after. So once we get to that Connect assignment after the next exam, and if we're looking at the book for help, sometimes you'll see it written H subscript 1. That's kind of the normal convention. We don't have to use numbers, so I just assume you use the letter A to make a little bit more sense here, right? So the alternative hypothesis is H subscript A. So I kind of already outlined this slide already. We either find evidence that goes against the null, and it goes against the null enough that we can reject it. Or we find evidence that, yeah, it goes against the null, but man, 49,000 isn't that far away from 50,000, so I'm not going to reject that as the true value. Or we find evidence that supports the null. That was like if I found an average income of 55,000, well, that supports the null. So if it supports the null, I'm not going to reject it. So kind of our two outcomes are we're either going to reject the null or we're going to fail to reject it. Now, we don't use the word except typically because what we're really saying is, well, we didn't find evidence from this sample, but if someone took another sample, potentially they could rule this out. So I'll try to make an analogy to a court case about how we think about this, right? Just so we can kind of get a good construct of hypothesis testing. So what are we trying to test with a court case? If there, let's say we have a murder case, right? We're trying to see whether or not the person is guilty. That's what we're trying to find. So what do? Well, what we're trying to find is our alternative hypothesis. So we're trying to find them guilty. The null would be the exact opposite of that and kind of stack the deck against ourselves. So what do? We assume that they're innocent, right? So the null hypothesis with the court case is we assume they're innocent, which means the complement of that would be that they're guilty. So the alternative hypothesis is they're guilty. The null is that they're innocent, right? If we can find sufficient enough evidence that goes against the null, right? So remember, we started assuming they're innocent. Well, if we find their DNA at the scene of the crime, they didn't have an alibi, they had motive to murder this person, then you're going to go to jail. We'll actually reject the null. If we have enough evidence that goes against the null, which is that you're innocent, we'll reject the null and say, well, no, you're not innocent, you're guilty, right? Now, if we don't have enough evidence, right, maybe there's no DNA at the scene of the crime, there's not really a motive, but maybe they didn't have an alibi. So it's like, yeah, maybe they could have done it, but there's no real strong evidence to say that they did. Then we fail to reject the null, and we just assume you're innocent and you go free. So that's kind of the analogy. We can kind of start to think about some of these, but we're going to be dealing with some numbers, right? But this kind of gets at the principle of what we're doing with hypothesis testing. Any questions up to this point? Yeah. Yep. Yep. Okay. Yeah. So actually, we'll dive into something here, and I'll answer that question as I work through it. But that's a good question. Okay. So we got this court case example down. Well, I'll come back to this slide in just a second. So because I want to get that question answered, and I do think it's a good point or a good time to bring it up. So when we're doing hypothesis testing, we said, okay, what I wanted to test for, that's my alternative hypothesis. So I'm going to say, is that population mean? I want to see, is it less than 7%? So what I'm going to assume is true is that it's greater than or equal to 7%, right? That would be kind of my null alternative hypothesis there. Well, what do I know is going to be true about my distribution of sample means? As long as I take a sample size over 30, which I think the example we had 36, my sample means should be centered around the true population mean. Well, I don't know what the true population mean is, but I've assumed it's greater than or equal to 7%. And before we leave, I'll kind of make a point as to why we do this. But for now, just take it at my word. We're going to use the very lowest value in that range, right? So we're going to say, okay, let's assume that it is 7%. If the true mean was 7%, and the way we'll write this is mu subscript 0. It isn't the true population mean, but it's what we've assumed to be the true population mean, right? It's coming from kind of our null hypothesis. Well, if I see a sample mean of 7.5, that supports the null. So do we have to do any work there? No. If it supports the null, why would we reject it, right? However, if we see something like 4.5 as my sample mean, well, that seems like it's pretty far away from that assumed true mean. And in fact, if I was given the population variance and I could calculate my standard deviation of my sample means, what could I do? I could turn that sample mean value into a z-score and find the probability that I saw something that far away from the assumed true mean, right? And let's say this probability ends up being really small, like 0.001. Well, then I'm going to look at this and say, well, look, if the assumed true mean is 7, right, if that was the true mean, the probability I saw this value from my sample was only 0.001. It was very unlikely. So what's probably true in that scenario? This probably isn't the true mean, right? It's probably more like the real population mean could be somewhere down here. Now if I think about, oh yeah, well now if I think about what's the probability I see this, it's going to be a much larger kind of probability, and you know, the probability was like 0.5 or 0.6. Well, that seems like, yeah, this is a very possible, like it may be, you know, I don't know, maybe this is like 5.2 or something like that. So these probabilities we'll eventually get to, this is really what's going to dictate whether or not we reject or fail to reject. Okay? We need to talk about a few more things before we get to that, but this is good because this is a good setup to think about this. Okay? So there's 3 types of tests we're going to do. What did we have? We had this one right here, where when we identified that null alternative hypothesis, the alternative hypothesis has a less than sign in it. Okay? So what we're going to call that, you know, this mu subscript 0, if I can get my mouse to show it, there we go. In practice, that's going to be a value, right? That's that assumed true value. Okay? So if we have in our alternative hypothesis a less than sign, we're going to call that a less than or a left-tailed test. Because only evidence on the left side of the distribution would go against that null, right? Whereas if we have a greater than sign in the alternative hypothesis, well now values that are on the left side, right, values below a certain value, well that's going to support the null. So the only values that support the alternative or go against the null if we have a greater than sign in the alternative hypothesis are going to be values on the right-hand side. So we'll call this a greater than test or a right-tailed test. Less than is a less than or a left-tailed test. And then if we wanted to assume that, you know, let's say we do that, the mean is exactly equal to 7. Well, this becomes interesting because now if I see a sample mean of 7 or a 4.5, that goes against my null. But if I see 7.5, that also goes against my null because I've assumed that it's just exactly one value. So for this not equal to test, what we'll do is we'll call that a two-tailed test or two-sided test. These are one-sided tests or one-tailed because only one direction matters, right? With a two-tailed test, seeing sample means on either side of that assumed true value would go against it. Okay? Now, one thing that I want to point out here is really the naming of these tests is based off of my alternative hypothesis. Greater than sign is a greater than or a right-tailed test. Less than sign, less than or left-tailed. Not equal to sign, well, that one's not quite as clear, but it's a not equal to or a two-tailed test. And as we work through more examples, I think this will become a little bit more clear. Okay. Any questions up to this point? So we haven't completely worked through how we're going to reject or fail to reject, but we're getting there. Okay. All right, so we've got these 3 different types of tests, and this, I'm going to kind of just mention a couple things from this slide because a lot of it's kind of pretty obvious. I mean, the first thing, you have to figure out if you're dealing with a mean or a proportion. That seems, you know, ridiculous. I think this step should be pretty easy, right? Because we can do hypothesis testing not just for sample means, but we can do it for sample proportions. Or sorry, not say for, using sample means and sample proportions. Figure out what your hypothesis test is. Is it a 1 or a 2-tailed test? We'll eventually, by the end of class, figure out why that matters so much. And then one thing I just want to point out and kind of notice, we have to have the equality sign somewhere in either our null or our alternative hypothesis. But kind of the normal convention is to always kind of put that into your null hypothesis, right? We have the equality sign here in the null, but not the alternative, right? And that kind of makes sense. That way, when we have that equality sign, we can use that very last value in that range as that assumed true mean. Okay? And like I said, we'll get to eventually why do I use 7 and not, 8.3, right? We'll talk about why. So before we do that though, we've already identified kind of what our null and alternative hypothesis was in this scenario. What we wanted to test for was whether or not an ABV less than 7%. So what we want to test for is our alternative hypothesis. We assume the opposite is true, right? Just like we assume people are innocent, stack the deck against ourselves, assume it's greater than or equal to 7%. So what if we had an example where we had an economist who wanted to test for whether the mean retirement age is different than 67? So what we want to test for is we say, look, I think 67, either I think it's too high or it's too low, but I don't think the average retirement age is 67. So I want to take a sample and see if I can reject this value. Well, this is what I want to test for. Is it different than 67? So I assume the opposite is true, which is that it's exactly equal to 67. So anytime you see this kind of term or this word different or different than, and you're supposed to identify your null alternative, that different than phrase should tell you it's a two-tailed test or a not equal to test, right? I don't care if I see that the mean retirement age is 68 or 64. I don't care if it's above or below 67. I just want to test for whether or not it's different than 67, either above or below. So here we would kind of have this not equal to or this two-tailed test. Okay. Any questions on that one? And a lot of the identifying is just going to come from working through more examples. So we're going to skip this stuff for today. We'll come back to this on Tuesday. So type 1 errors, some good memes saving for Tuesday. So how do we actually conduct this hypothesis test? Okay. So this is where I'm going to walk through this. And we'll use this same kind of example. So what we're going to do, we have this setup. My marker is kind of dying on me, where we know that if my null hypothesis is that the mean is greater than or equal to 7%, and the alternative was that it's less than 7. So I'm going to use that assumed true mean of 7. And if that was the true mean, my sample mean should be normally distributed around it. I then see this sample mean of 4.5. Okay. So what I'm going to think about is, well, how unlikely was it, if this was the true sample mean, how unlikely was it that I saw 4.5 or something even further from that assumed true value that would go against my null hypothesis? So that last part is important. When I say, what's the probability I saw a sample mean that went against the assumed true mean that I did, or anything even further from it that went against the null, well, only the values to the left of it would go against the null. I could see something that was equally as far away from that assumed true mean on the other side, but those values would support the null. Right? And that becomes important when we get to two-tailed tests, which is where we'll kind of end there eventually. But for now, okay, so now what I'm thinking about is, well, look, I know that if I could figure out, or if I was told what the population variance is, I could very easily turn this value of 4.5 into a z value, look that up in the table, and find that probability. Okay? So we had an equation for this already, which was take the sample mean value you're interested in, subtract the mean, and divide by that standard deviation of my sample means. Well, the only difference is now we don't have a population mean, we have a assumed true population mean. Okay? So this is going to be the equation that we use to calculate, and it is a z value, but we're going to end up calling it a z statistic because it's a test statistic. And when we get, when we're doing hypothesis testing, the test statistic refers to the fact that, yeah, we're not using the true mean, we're using an assumed true mean. Okay? So this is our test statistic. But the test statistic is a z value, so it's a z statistic. We can still look it up in the standard normal table and find the probability that we saw a sample mean that was this many standard deviations away from the assumed true mean, or anything even more standard deviations away. And that probability, we're going to call that our p-value. So we'll have this, which we'll call kind of our, and I'll usually start writing it as like z-stat, so it's a z statistic, but it's using something that we already knew, right? Which is that if I have a sample mean, to turn that into a z-score, I'll subtract the mean, which now is just an assumed true mean, and divide by the standard deviation of my sample means. And we know how to look up p-values because they're just probabilities, right? They're probabilities coming from a standard normal distribution. Any questions on that up to this point? Okay, all right. So the next kind of idea, once I have this p-value, let's say that the probability I saw 4.5 as my sample mean, if this in fact was the true population mean, but that probability is only 0.03. So kind of similar to confidence intervals, what we're going to start doing is, okay, look, I know that's pretty unlikely, but is it unlikely enough? So ahead of time, before we even started this process, what we're going to do is we're going to set something, we're going to set alpha. Maybe we set alpha to 0.05. So what we're really saying is, if I find that the probability that I saw my sample mean, or anything below it, right, is less than 0.05, then I'm going to reject this value as the true mean. Because it was so unlikely, it's below this threshold that I set. So alpha is going to have to be given to you, or you're going to set it kind of as the researcher. And then ultimately, the rejection decision is going to be, once you find this p-value, if it's less than your alpha, you'll reject, right? Here, the probability that I saw 4.5 as my sample mean, if this was the true mean, that probability is only 0.03 or a 3% chance. Well, that's less than this kind of 5% cutoff. Oh, you can't read it? Okay, sorry, hold on. So when I'm referencing 0.03, this is the p-value, right? That was that probability that I saw this test statistic or anything below it, okay? So we'll call that our p-value, okay? So that 0.03 is less than this threshold we set. So we, in this case, would say, okay, we can reject that 7%. And that can't be the true. It's unlikely that, given what we saw from our sample, that this is in fact the true mean. We can reject that as a possible value for the true mean. Okay? And that's kind of the complete kind of that's where we stop, right? We made our rejection decision. Now the reason, let's say instead this was 0.13. Well, that's not below the threshold I set. And so I'd say, well, yeah, it's not very likely, right? It's a 13% chance I saw what I did or anything further from that. But 13% is higher than this threshold amount that I made, which was, it has to be 5% or less likely for me to reject.
I have a question.
Yep.
So are we rejecting it because the sample fell within something that was so unlikely, so that means it can't be 7?
Yeah, that's
That's basically the gist. Okay.
That's like if you had to like kind of wrap it up, we're rejecting because if the true mean was 7, it's so unlikely that we saw 4.5, right? There was only a 3% chance that we would have actually seen it. And we're okay basically rejecting if the probability of the sample mean that we found is anything less than 5%. Right? We're saying anything less than 5%, if the probability of seeing that sample mean is anything less than 5%, it's so unlikely that this probably isn't the true mean. It's kind of like before I said it's probably not the true mean. It's probably more like this is the actual distribution of my sample means. It's probably centered around a lower value. Right? Does that answer your question?
Yes, that makes a lot of sense, actually.
Perfect. So at this point, I want to point out something else. So here we determined we rejected, right? So I said earlier, why am I using the lowest value here, right? Like, why didn't I choose 8.3 or 7.9 or hell, 20.5, hopefully it's not an ABV of 20 something, but, right? Why did I choose that cutoff value? We'll think about this process of how we found the p-value. Okay. Let's instead assume that instead of 7%, we chose the value of, and actually I should do this in green here so we don't confuse it with the other stuff that we do. Let's say I chose 8%. Well, if I think about the distribution there, now when I turn this into a z-score, it's going to be a further number of standard deviations away from 8, 4.5 will be more standard deviations away from 8 than it was from 7. So my Z statistic would be like larger in absolute value. Since it's negative, it's going to be a larger negative value. So my p-value would be smaller. So if I can reject 7, well, if I try to test against the value of 8, I'm going to end up with a smaller p-value. If 0.3 is already less than 0.05, a smaller p-value is definitely going to be less than 0.05. So if I can reject the lowest value in this range, I can reject every other value, because as I move that mean to the right, I'm just going to end up with a smaller and smaller p-value. Okay? Now, if I can't reject 7, it's possible that if I fail to reject 7, I could reject 8. But the idea is if I can reject 7, I can reject every other value above it. Okay? Any other questions up to this point here? Are we at in time? Oh, okay. We're good. So you're not given the p-value, you'll be given this threshold alpha, right? The p-value we can calculate. Now I don't have all the numbers here because what's the only thing we were missing? I think we actually knew the sample size was 36. I didn't give you a population variance. I think if you go far enough in the slides, and we're not going to quite get there today to work through this completely, I don't think. But let's say I had a sample variance of, 3 or something. Well, then I could calculate the standard deviation of my sample means. I could plug that in down here. This would be 7. This would be 4.5. I'd have an actual Z value. I could look it up in the table, and that's how I would find the p-value. I was just using 0.03 as just like a number that we could kind of use, so I didn't just kind of keep referencing the nothing. I don't know what this actually ends up, what this p-value actually ends up being. My guess is it might be lower than 0.03, right? Depending on what that standard deviation is. So So for this next exam, yes. So for the next exam, we're not going to cover how to do this in Excel. Right? Would it be easier in Excel? Not necessarily. I mean, okay. So I guess I should say this. It's not that I won't. I think we'll have time next week to look at how we do this in Excel. I am not going to expect you to do that like on a homework assignment prior to the exam, right? But we will take a look at how we do this. And honestly, we already have all the components. We've already talked about everything we need in Excel after the confidence interval stuff to be able to do this, right? It's just kind of making those functions kind of fit what we're doing here. But yeah, we'll kind of include that next week to see what it looks like in Excel and to match up with this. Yep. Yeah, if we'll find that kind of helpful. So finding that p-value is only going to be one approach. There's going to be 2 approaches that we can do hypothesis testing, or we can use to do hypothesis testing. I just explained the first one. The second one's coming next week on Tuesday. Right? So we worked through this whole example, right? We talked about kind of different values. These ones would support the null. These ones go against it. But do they go against it enough, right? And the idea was once we find this p-value, we can determine if it went against it enough based off of this threshold we set originally. Okay? So we talked about calculating our test statistic. These slides are really a summary of what we just went through. I just think that it's a little bit easier to see me kind of work through it by hand. So we've got our test statistic equation. Notice instead of the standard deviation of my sample means, very similar to confidence intervals, I could plug that equation that I know was going to give me the standard deviation of my sample means right into my test statistic equation. So I can calculate it all at one time using this, or just like confidence intervals, I can calculate the intermediate step first, which can sometimes make it easier, especially with a calculator making some parentheses mistakes. Okay. We already talked about kind of finding the p-value. Here, this slide, I'm going to kind of make some sense of it. That's going to be how we're going to end class, is making sense of this slide right here. So why does this kind of greater than z, less than 2p? Okay, what's going on here? So we walked through an example of how to find that p-value for a left-tailed test, right? Because only values that were below 7%, were going to be values for which they would go against the null, or that we could even possibly reject the null, right? And that's because it was a left tail or a less than test. So to find the p-value for a left tail test, once you found that test statistic, you had to find the area to the left. That was your p-value, right? The probability you saw something this many standard deviations below the mean or anything even further below. For a,
I have a quick question.
yep,
How do we come up with the alpha? Will that be given, or do we
you have to be given the alpha. So one thing that we'll likely also kind of start talking more about next week, alpha is going to be very similar to confidence intervals. We're almost always going to use these 3 alpha values, which you can imagine, just like confidence intervals, okay, we can reject at the 90, 95, and 99% levels of confidence. Right?
Okay, yeah. Thank you.
Yeah, so we're going to be given these in a problem or whatever, but yeah, these are the 3 that we're really going to use. Just like with confidence intervals, these are really just the 3 levels we use. So we went through a left-tailed test. What if we had a situation where, and we could set up the exact same way, but now I say, okay, now I'm going to assume that it's less than or equal to 7%, and the alternative is that it's greater than 7. So now only values on the right-hand side are going to go against the null. So maybe instead of 4.5, let's say I see 8.5. Well, I can go through the exact same process, right? I can turn that sample mean value into a z statistic. But now for a right-tailed test, remember the p-value represents the probability that I saw something this many or this far away from that assumed true mean, or anything even further that goes against the null. Well, now the only thing that goes against the null are values on the right-hand side. So now once I find my test statistic, my p-value is the area on in the right tail. That's why we call it a greater than, or I'm sorry, that's not an equality, greater than or a right-tailed test to find my p-value. So now when I find my test statistic, it's the probability of seeing that test statistic or anything greater, right? Anything to the right. But in terms of, the steps, it's very similar, other than like when I go to the table always tells me the area to the left. So with a right-tailed test, it's kind of like you have one more step, which is to find the p-value. When I find the area to the left of my test statistic, I'll have to subtract it from 1. But that's already something that we've kind of hopefully gotten used to. We've been seeing a lot of these different problems that we've been working with, kind of going back to the distribution of sample means. So right-tailed test, we want the area to the right of my test statistic. The last one that we have to get through, and we'll kind of end on that, or end after this, sorry, is what if I assumed it was equal to 7%, right? So now I'm saying, okay, I'm going to assume that true mean is equal to 7. So my sample means will still be normally distributed around that. But now the test is, well, I just want to see, is it not equal to that? So I assume it is equal to 7. So maybe I see, let's actually use that same sample mean value of 4.5. And you might think, okay, well, this is easy. It's the exact same thing that we were doing before when we did this, right? So I turn this into a z statistic. I find the probability that I saw something this far below that assumed true mean, or anything even further below that went against the null. And when I say below, what I actually should say is, what's the probability I saw something this far away from this assumed true mean, or anything even further away that went against the null hypothesis? The problem is, this is not my p-value, because the p-value is the probability I saw something this far away from the assumed true mean, or anything even further away that went against the null. Well, this is 2.5 away. It would have been equally as likely for me to see 9.5 as a sample mean. And that would have went against my null hypothesis now. Because for a two-tailed test, evidence on either side of that value matters. So now it's like I have two tails, almost starts to look like confidence intervals. So this won't be my p-value, but remember, it's something that was equally as far away, so it's actually going to be like the same number of standard deviations away on the other side. So if I find my test statistic and I find the area to the left of it, well, this actually just represents half my p-value, because it would have been equally as likely for me to see something above that assumed true mean that went against the null as well now with a two-tailed test. So when I find the area in one of these tails, instead of, I won't actually see this, right? I'm actually only seeing 4.5, right? So once I find that area for a two-tailed test, well, if that's half my p-value, how do I get my total p-value? I just multiply by 2, which is where this comes from, right? So if I have a negative test statistic, right? If I saw 4.5 and I have a negative test statistic, it's something that's below that assumed true mean, I'll find the area to the left and multiply by 2. If instead I'd seen something that was above that assumed true mean, I'd have a positive test statistic, so I would have found the area to the right, but then it's still a two-tailed test, so I would have then multiplied that by 2. But they're both the same value, so either way I would have kind of ended up with the same result. So that's why the mathematics, when it's written down mathematically, it looks a little bit, okay, well how come sometimes it's above 0, sometimes it's less? Well, it's because we only see one sample mean, right? It's just that the process of finding the p-value for a two-tailed test is the same no matter if we find a negative or a positive test statistic from the sample mean that we see. So greater than or a right-tailed test, you find your test statistic and you get the area to the, there we go. For a right-tailed test, you find your test statistic and find the area to the right, that represents your p-value. Left-tailed test or a less than test, you find your test statistic, area to the left is your p-value. Two-tailed test, well, it depends. You might end up with a positive or you might end up with a negative test statistic. It depends on the sample mean you see. But once you find the area that's in the tail, you just multiply it by 2 because you have two tails for a two-tailed test. What's something else? There was something I wanted to say here. One thing to keep in mind also for these two-tailed tests, like I'm only seeing one of these samples, right? So it looks like here on this picture that I have two test statistics. No, I don't, right? I'm only ever, in any given problem, I'm only going to see one of these test statistics. And another thing I'll start saying is, because, for right-tailed test, it's the area to the right, left-tailed test, it's the area to the left, depends for a two-tailed test which side it is. I'll say the p-value is the probability you see this test statistic or anything more extreme. That way, if it's a negative test statistic, more extreme is going into the left tail. If it's a positive test statistic, anything more extreme is going into the right tail, right? So it kind of covers any possible type of test that we would have if I say it that way. So more extreme or larger in absolute value. Okay. So I know, and for all of them, the rejection decision is if your p-value is less than alpha, you reject. Right? That applies to not just the left-tailed, but to all of them. So I know this is a lot. So this is just kind of the introduction of getting the ideas of what we're doing with hypothesis testing down. Next week, Tuesday and Thursday, we'll just be going through more examples, like with some actual numerical examples. We'll work through different types, left, right, two-tailed tests. I'll introduce the critical value approach, and I think by kind of the end of next week, we'll have a pretty good, hopefully, understanding of kind of what we're doing with hypothesis testing. We'll have seen a lot of examples. I'll bring some examples from Excel in that we can use. And when I say the exam is going to be kind of the following week, not sure exactly when we'll do that. I might do that Tuesday as a review day and put it towards the end of the week. I'll have a little bit more of an outline for the dates of the exam kind of next week, right? I'll bring that Tuesday. We'll have a little bit better idea of what I want to do with that final exam the following week, okay? But I realize that this is a lot for today, so don't feel like you have to have a perfect understanding. I'm just going to keep explaining it, going through more examples, explaining it in different ways. So hopefully by the time we get to the end of next week, we'll feel pretty comfortable with these hypothesis testing examples, okay? All right, a little bit over time. No online quiz today, as I mentioned at the beginning of class. You will have that Learn Smart to just read more and kind of get more information about that, about hypothesis testing that'll be due before we start class on Tuesday.